Today we're going to be talking about discrete random variables. And for example, a random variable we could consider that is discrete because the outcomes are 0, 1, 2, 3, etc. They're the integers, are the number of cats owned by a randomly selected person. So let's pretend that we collect data on this and that what comes back is 0, we have a 1, we have a 2, we have another 2, we have a 0, we have a 1, another 0, a 2, a 2, and finally we have another 2. So a lot of people with cats here. Okay. So if we go ahead and we were to write this out, we can form the probability just using the empirical probability formula. So x versus p of x. Okay, the outcomes are x are no cats, one cat, or two cats. Okay, let's make that a little bit smaller. We see that the probability of 0 cats, that there are 3 zeros in this data set. So we have 3, and the total size of this data set is 10. So that's equal to 0.3. We have 2 ones, so that's 0.2. And we have 5 people with 10 cats. That's a lot of cats. And so that's 0.5. The first thing that I'm going to just note is that we have what's called a valid probability density function. So I'm going to tell you that p of x is a valid density function if we have two properties. One, p of x is greater than or equal to 0, and I'll also say it's less than or equal to 1, because it doesn't make sense to have that property that is bigger than 1. And 2, if all the probabilities, total probability, and how we can calculate total probability formally is this sum from minus infinity to infinity. That's every possible outcome of x. That equals 1. These are the two conditions to be a valid probability density function. So it's common to see a question like this that says, here's x, here's p of x, but we forgot what one of the probabilities is. And here, if we want to determine the unknown probability, all that we'll do is we'll use this second property that 1 is equal to p of x equals 0 plus p of x equals 1 plus p of x equals 2. All the other probabilities are 0. Okay, and so we get 1 is equal to 0.3 plus 0.2, and then we have our unknown probability, and solving this equation tells us that it's equal to 50%. Okay. A second thing that I'd like to go over is just to calculate the average Here, the average, what we've learned throughout our life is that just that we can calculate the average by adding up the data. So 0 plus 1 plus 2 plus another 2 plus 0 plus 1 plus 0 plus 2 plus 2 plus 2 and dividing by the total sample size, which is 10. Um, so let's go ahead and add this. And that's going to be 12 over 10, which is 1.2. And let me just check that, just to be safe, because I can make mistakes. And that is 1.2. So the average is 1.2, but I want to rearrange this. So I'm going to take this original inequality, this original equality right here. I'm going to rearrange things. I'm going to put the 3 zeros together. And now I'm going to put the 2 1s together. And I'm going to put the 5 2s together. Now, I think that I can write this as 0 times, well, 0 occurred 3 times, so that's going to be 3 tenths plus 1 times 2 tenths plus 2 times 5 tenths. And that's nothing more than this, the sum of x times its probability. And here, just to make it clear that I sum up all the probabilities, I put minus infinity times infinity. This is called the expected value, or the mean. And it represents nothing more than the average value. Now, the difference between a sample average and an expected value lies in the fact that when we do an expected value or mean, the probabilities should represent population probabilities. And in a sample, they might have some random variation to them. Okay, but this is the meaning of this formula and where it comes from. I'd like to just mention that this is called the expected value at the first moment. There's also e of x squared. That's the summation from minus infinity to infinity of x squared times p of x. You can also formulate the expected value of the kth moment, or x to the kth power, and that will be x to the k times p of x. And finally, you could also formulate the expected value of a function, which would be this. And that's the average value of a function. Okay, so those are kind of future steps that we might take and look into. But two big concepts is first the expected value or mean or average, if you will, but average should be in quotes. And the other one is what it means to be a valid density function. Thank you very much.